Good morning, everyone. Today is July 4th, Independence Day here in the United States. Yay! Okay. Watched Hamilton last night on Disney Plus, so that was terribly educational. I'm not quite sure I get what the big deal is. But in any case, this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu. For those who are watching on the live stream, I don't think anyone is there yet. Maybe because we started a little bit late. But feel free to put your comments in the chat, and I'll do my best to try and get to those. So today we have on the live room here, we have Ian, and we have Alistair, and we have Bob, and we have James just came in here. So welcome everyone to today's Science Chat, and we're celebrating the 4th of July here, Independence Day. Okay. So, but Bob has told me that he has some slides on the magnetic field. I've been leading the discussion recently about what do we think about the magnetic field. This is once again one of those mysteries that the mainstream, really doesn't have a good explanation for, in the sense that they haven't really provided a motivation for why the magnetic field does what it does. I mean, they can explain what or predict to a large extent how the magnetic field works, what causes the situations to explain the intensity of the magnetic field and stuff like that. I mean, we can make predictions, but that doesn't really explain, the why. Why? Maybe the how. This is the problem. It explains the how, but not really, the why. Why does an electron deflect in the presence of a magnetic field? It's not enough to say, how that works, but why that works. So Bob, I was hoping maybe you had some insight on that, or maybe you're doing more on the why or the how. But
yeah, I have some slides which I could share and go through. It's a little meandering, and at times I'm sure you'll think that I'm off topic, but I try to bring it back. If nobody else has a really hot issue or topic, I'm more than happy to go through the slides.
Let's go through the slides. Have you done the screen share before?
I think I have. Let's see, screen share. Let me see, share screen.
Yeah,
you friendly share screen.
Just select your entire desktop usually.
Share.
And, okay, I've got your shared screen. Now I can put it up.
And
there we go. You see your.
Unfortunately, I can't see you, and I can't see the chat room. So if there are comments, I can't see them. Feel free to interrupt me, and either with your own comments or comments from the chat, because in this full screen mode, I can't see anything other than my slides. We ready?
Yes, we are ready.
Okay.
For some reason, I keep on dropping off. So if that happens, don't panic. I'll come right back. So.
Well, the first thing I wanted to point out is that there are many different meanings to the word field. For example, in mathematics, a field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers do. Now, that's from Wikipedia. And actually, in mathematics, the definition of a field gets very, very technical, and I'll spare you all from that. For the question, what is a magnetic field? We are talking about, in my opinion, the electrodynamics field. And I will define that electrodynamics field to be the force on a test charge body per unit charge. And if we were to take that as our definition of electrodynamic field, then the magnetic induction field B would not qualify because its units are not that of newtons per charge. So you can't get just a charge times the magnetic induction field that does not equal a force.
Now, what do you mean
So
by induction? I think you lost me there. What's the difference between?
there's
Well, I just don't know what you mean by that.
all right, it's the name of this thing B. Okay, there's in classical electrodynamics, there's a B and there's an H. And people call H the magnetic field and B the magnetic induction field simply to distinguish between B and H.
Yeah, what is the
And so
difference
we
between B and H?
just offhand just say, oh, the magnetic field B. I was trying to be a little bit more picky and call it the magnetic induction field. Yeah. Okay.
You mean conventionally just the magnetic field, the same thing that you see when you sprinkle filings around a magnet is like B, isn't that right?
Yeah, if you want, I'd be happy with that. I'm not going to go into that kind of detail at this point. So I'm just pointing out that, yeah, there is a terminology issue from that point of view. Okay, now, you know me, I've talked a lot before about Weber electrodynamics. It's the thing that I'm focused on these days in all my research. So the Weber electrodynamics force equation for the force between two discrete charged bodies can be written as follows. And I have F is equal to gamma and then Coulomb force Fc, where gamma is called the Weber coupling coefficient and EC is the Coulomb field. The Weber coupling coefficient indicates how the force on the test charge body changes depending on the kind of motion of the test charge body with respect to the source charge bodies associated with the Coulomb force in the Coulomb field. Now this gamma coefficient here has a constant term, a velocity dependent term, and an acceleration term. And that I give that here just to be complete. A dot over something means a derivative with respect to time, and two dots means two time derivatives. But anyway, the reason why I bring that up is because static friction is friction between two or more solid bodies that are not moving relative to each other. And you'll find this as F is equal to mu times the normal force. But there's also a kinetic friction coefficient, mu sub k, also known as dynamic friction or sliding friction, which occurs when two objects are moving relative to each other. Okay? So this idea that you have a force, Coulomb force, and some kind of coefficient multiplying that Coulomb force, and that coefficient depends on perhaps a constant, perhaps a velocity, perhaps an acceleration. That's not unusual in physics, i.e., here's an example from classical mechanics, static and kinetic friction. That is, the coupling interaction force between two objects is different depending on the relative motion between the two objects. Now, I consider the electrodynamic force to behave similarly, but of course not exactly the same. Specifically, the force on a test charge body due to the electric field associated with a source charge body depends on the relative motion of the two charged bodies. It is this relative motion dependency of the net force on the test charge body that makes it appear that there is something called a magnetic field. In fact, the magnetic field is simply the dynamic coupling of the test charge body to the source charge bodies associated with the Coulomb field. The Coulomb field in this Weber field approach is the only real physical field. And again, I just give the equation to refresh your memory from the previous slides. Now, W. Hooper's electrodynamics has been discussed on the Saturday chats before, and so I just wanted to point out that Hooper identifies 3 electric quote-unquote fields, but note that each of his 3 electric fields depend on a different relative dynamic, a constant dependence, a velocity dependence, and acceleration dependence. So I want to bring in at this point as well, Occam's Razor. Entities should not be multiplied without necessity. Is it really necessary to call these 3 different electric fields? Is that necessary, or is there only one field and a dynamic coupling? So from Hooper's book, New Horizons in Electric, Magnetic, and Gravitational Field Theory, here's a page from his book, which I got from Bill Lucas. Thanks very much, Bill, if he's out there listening. And so Hooper is identifying a Coulomb field, written like this, a motional electric field, and a transformer electric field, which is a partial derivative with respect to time of the vector potential A. So here's my summary of Bill Hooper's E fields. And on the right, I have the derivative with respect to time, how many derivatives with respect to time for each of Hooper's electric fields. You can see the first one, the Coulomb field, has no time derivative. The motional electric field has one time derivative, that is, it depends on velocity. And the transformer electric field depends on the second derivative with respect to time, that is, on acceleration. And although it's not explicitly shown here, this vector A function is velocity dependent. And so if you take the time derivative of a velocity, you get the acceleration. So this is acceleration dependent. We explain these differences as different couplings to the Coulomb field based on the relative dynamics of the charged bodies, not separate fields. Another approach, consider the multipole expansion of the scalar potential function. This is a scalar potential function in regular classical electrodynamics. And from this function, we get the Coulomb field by taking minus this gradient of this scalar potential function. But if you look at the textbooks, if they use this thing called multipole expansion of this 1 over r dependency here, the multipole expansion of the scalar potential function has an infinite number of terms. And I write that here, constant term, this term, plus dot, 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 an infinite number of terms. Okay, so then is each of these terms to be a new scalar potential function? And then if so, is this then each of these terms, then when you take minus the gradient of these terms, are you going to say that these are new fields? Are you going to say this is a monopole field, a dipole field, a quadrupole field, dot, 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 off to infinity? So now are you talking about an infinite number of fields? So Hooper's approach and this expansion approach seem to result in multiplying fields without end. Again, Occam's Razor, entities should not be multiplied without necessity. Again, in Weber electrodynamics, when properly derived, one form for a magnetic induction function B, not a physical field, a function, due to individual source charge bodies, can be written like this, a velocity cross product, the Coulomb field. So no new physical magnetic field is actually needed. It's not needed. Now, it may be mathematically convenient and it makes the mathematic calculations easier, but boy, is it very misleading. That's why I always try to go back and emphasize it's the Coulomb field. Another perhaps tangent, but it will tie in. Note that the superposition principle of the Coulomb field does not mean that fields are canceled. It simply means that the net Coulomb force on a test charged body sums to 0. That's not the same thing as no Coulomb field. When there are more than one source charged body, you can have the case where the constant contribution sums to 0, but the dynamic terms do not sum to 0. So here's that Weber's force equation again. Now I've put in sums for each of the charged body making up, for example, a real magnet. And the three terms, the first part here is constant dependence, velocity dependence, acceleration dependence. But for a magnet interacting with another magnet, the first summations is 0. And that's because the magnets are charge neutral, while the other terms do not sum to 0. Hence the appearance of so-called magnetic field. So these other terms, these interacting magnets, you have to take every single bit of charge that is in motion and sum them up like this to get the interaction of the two magnets. And the summation only involves the Coulomb field. Even though these are charge neutral bodies, so that this first term sums to 0, these other terms do not sum to 0, and hence give rise to a net force on one magnet due to the other magnet. The magnetic effect is simply the sum of the coupling.
Bob?
Yes? Yes?
Do you mean that they do not necessarily sum to 0, or that they absolutely never sum to 0?
I put in that they do not necessarily sum to 0 only because I can think of the same material not yet magnetized. Okay, so now
you answered my question. Thank you.
Okay. So the
in other words, they could sum to 0.
They can, yes.
They could at some point sum to 0, but
that's right.
In general, you're saying that they probably don't. Probably most of the time they do not sum to 0. That's I guess what you're saying.
When it's a magnet, so that the magnets have been magnetized, then the direction of these motions are aligned in certain ways so that these sums do not sum to 0. If they are not magnetized, then they can, yes, potentially sum to 0. So the magnet...
Thank you.
Yeah, sure. The magnet effect is simply the sum of the coupling of the test bodies to the Coulomb field associated with the source bodies. Just because the first sum is 0 does not mean that there is no Coulomb field to couple to in the other terms. The Coulomb fields may approximately sum to 0, but the fields are not canceled in the sense of not existing. And then I just threw in some pictures here of charge in motion in a couple of different models for an atom. Kind of a traditional point of view on the left, which I think is very bad. And then from Bill Lucas's Common Sense Science website, a different kind of model for a neon atom. But these little toruses here are current loops. So again, charge is still in motion, if I understand his model correctly. So here's an experiment that Franklin happened to mention last week of just a piece of wire with a current through it, and let's have a charge moving. And what about that charge moving in this magnetic field that's caused by the current, and the charge deflects in a certain way, et cetera, et cetera. Anyway, so let's look at that experiment. Consider a wire carrying a constant current. Position a charged test body some distance from the wire, having a velocity, in this case in the positive z direction. question, what is the force on the test charge body due to the constant current in the wire? Note, this is an idealization. The real situation is far more complicated, and I will mention it, some of those complications a little bit later. We go back to the Weber force on the test charge body, and we do the sums, again, because the current carrying wire is assumed to be charge neutral, which is a very bad assumption. Then the first summation is 0, while the other terms may not be 0. And in fact, if you do the math and apply some additional approximations, for example, use a continuous charge distribution, lambda sub s, for the wire and for the current, use integration and then use integrals instead of summations. Also, the approximation that the conductive electron speed is very small in currents, we get the following result. I've done this calculation in all its gory details. It's really kind of a pain, but this is the result that I end up with. I get out my Jackson or my Griffiths classical electrodynamic textbook, and I look for their calculation of that same experimental setup. They use the Lorentz force term for the force instead of the Weber force, and they also find exactly the same thing. The difference is that Weber's approach does not require the concept of a physical magnetic field. Only the Coulomb field and relative motion of the test charge body with respect to the source charge body is needed. So here's some of those complications that I mentioned. For a real wire carrying a constant current, there is a surface charge distribution along the length of the wire. So this V is a voltage source, like a battery, and it's very much polarized. There's a surface charge density out here, even though this is carrying it, is a charge neutral wire carrying a constant current. There is also a surface charge along the length of the wire. And it doesn't matter the orientation of the wire. So that's a huge complication to carrying out this kind of experiment. Here's a photograph of it. This is particles of semolina polarized due to the external magnetic field and align themselves with it analogous to iron filings mapping a magnetic field. This black line in the middle is a wire carrying a constant current. Experimental mapping of the external magnetic field, straight conducting, carrying a steady current. Okay, and these are from Asis's book. Additionally, the test charge body will induce image charges in the conductive wire. So the experiment, although seemingly stated very simply, is extremely complicated in reality. It is not easy to perform the experiment with a stationary or moving test charge body and a current carrying wire. So the point here was, please be aware that when we start talking about these kind of experiments and these kind of derivation and results, we're talking about very idealized conditions that do not really represent reality at all. Okay, so then perhaps what the real fundamental question should be is not what is a magnetic field, because in my opinion, and as I hope I'm showing here, there really isn't such a thing as a physical magnetic field. But maybe the question should be, what is a Coulomb field? Now, there are many models attempting to answer this question. My favorite at the moment is Paul Laviolette's reaction diffusion model. His model is based on open system theory and chemical reaction diffusion-like systems. In his model, he considers the ether or vacuum space to be composed of etherons, which I'll label as ABC, And as in chemical reactions, we might have, for example, an A etheron combined with a B etheron results in a C etheron. That's the kind of thing that his model for physical reality is. Here, a suggested expansion of the G model, he calls this his model G, ether reaction scheme, as it would appear disposed along a dimension T. Now, G, X, and Y ons mark the domain of physical universe. So he has these A and A prime etherons coming in to a domain. They combine to generate G, meaning gravity, X and Y, which he uses to define electric fields. And that defines our physical reality domain. These are not permanent. They decay, they recombine, and then out of our physical reality goes Z, Z primes, or omegas, omega primes, etc. And this is very much as in chemical reactions. As in chemical reactions, it is possible to form waves in stable patterns. Okay, so this is a real photo of a chemical reaction where there are chemical waves and potentially stable patterns. In this model, a force is a result of a gradient in the concentration of the GXY etherons. Note that it might be the case that the geons responsible for gravity in this model may move towards higher concentration of geons, up a geon concentration gradient. That's my speculation of Paul's model, model G. I have to go back in his books and really dig out if that's really the way he thinks of geons or not, but that's a possibility. If that's the case, this would then be similar to what James mentioned last week about the work of Alex Dmitriev on gravity anomalies when objects are heated. Yeah, maybe. Anyway, in Paul's model of these reaction diffusion systems, it's possible that the concentration of these Y-ons and X-ons would be such that they form a stable, steady-state dissipative soliton, and that would be a charged body. So here we have ... this dash line here being a normal vacuum concentration of exons and Y-ons. And these graphs that he has here indicating a higher concentration of Y-ons and a lower concentration of exons form in this shell-like structure extending out toward infinity. He would recognize that as a charged body, like an electron or a proton. And then switching the concentrations, a high X and a deficit of Y would be the opposite charge in his model. Anyway, if anyone's interested in that kind of model for what is a Coulomb field and charged bodies, Paul has a nice book out called Subquantum Kinetics, a Systems Approach to Physics and Cosmology. So anyway, coming back to what is a magnetic field? It is really the Coulomb field together with a dynamic coupling coefficient that depends on the relative motion of the test charge body to the sources. And the Coulomb field may be a gradient of concentration of etherons as in a reaction diffusion system. The elementary charged particles may be stable reaction diffusion dissipative solitons that we do know exists in chemistry and chemical reactions. And this is very much like a source sink model for the electric field, but it is reaction based and nonlinear. And so that's all I had. I thank you for your attention.
Okay, thank you very much, Bob. So I was wondering, did anyone have any immediate reaction to what Bob said there?
Just maybe an immediate reaction, Franklin, would be, well, Thank you very much, Bob. I mean, it was quite an illuminating presentation. But as I think perhaps I have intimated before, it's one maybe somewhat arbitrary system to take the electrostatic field as being fundamental, and then to build upon that the electrokinetic elements to give the magnetic field. I mean, one could as easily take the magnetic field to be fundamental. I mean, one could, and by the way, I normally take H to be the correlative of E rather than B. So I take the electric field strength and the magnetic field strength as being correlatives, and then I take the electric displacement and the magnetic induction. But one could formulate an equation, something like force is equal to m1 m2 over 4 pi mu naught r squared, where m1 and m2 are sort of admittedly separate isolated magnetic pole strengths, not the charge q, and mu naught would be the magnetic permeability. So one could actually deduce a force from the field vector H, and then one could work backwards, presumably, and find the electrostatic or the Coulomb forces from that. So that's just one comment. The other comment is just briefly on the Weber system. I mean, I'm just wondering if you, and it's interesting that it gets the same result as Maxwell. You've done that detailed calculation, but if you have all these velocity dependent and acceleration dependent terms, I'm wondering why one doesn't have the third derivative, fourth derivative, the rate of change of acceleration, the rate of change of that, whether one stops at the acceleration.
Yeah, that's a very interesting question, which I was considering while I was writing my slides on Hooper, and saying that the first Coulomb field has 0 derivatives with respect to time. His motional field has the 1 derivative with respect to time. His transformer has second derivative with respect to time. And I go, well, what about the third derivative? What about the fourth derivative? The joust and the jolt and the whatever the physics terms are for those higher derivatives. Yeah, I don't know why it would stop. You would think that maybe there is. And to your comment about you could use the magnetic instead of the Coulomb field as the fundamental, I'm not so sure. I'd like to see that done. I have used, for example, Balanis has a textbook on electrodynamics where he postulates or uses magnetic charges just to complete the symmetry of Maxwell's equations, etc. And he seems to, then combine things, and things work out very nicely, assuming these kind of magnetic charges rather than electric charges, and combines that all together. But I think it would be interesting to start with that. Why not having a magnetic and start from that point of view? Interesting question. Yeah.
Thank you.
Yeah, so Ian, you're kind of proposing that there is a fundamental magnetic field. Is that what you were trying to say there?
Well, I suppose the import of my question, Franklin, was really that mathematically you could just as easily start with a magnetic field and work towards the electrostatic field. Now, the question of what is really fundamental is, I thought Bob might argue that. He might say, well, physically, I think this is more fundamental. But that's really a whole question in itself, and we would need to do more experiments.
Yeah, coming to mind as being more fundamental, it strikes me that you can have a monopole of an electric field, but not of a magnetic field. Magnetic fields start with dipole. I don't know of a monopole magnetic-like arrangement, and that may be why the electric is more fundamental. Maybe. I'm not saying anything absolute.
Exact point. as you were speaking, Bob, and I also was thinking of the contrary claim of people like Bill Lucas that magnetic monopoles are easily demonstrated on things like fridge magnets and other experiments and so on. But I was thinking of that point, and that may indeed be why historically, we started with the Coulomb field, and there may be a fundamental reason for it, but I think we need to talk for analysis. So I was merely saying that mathematically one could start with one and arrive at the other.
Okay, all right. I mean, personally, I think, yeah, you do need to kind of think about what is really fundamental here. And let's see, let me get a camera going here.
Yeah, the fundamental question in classical electrodynamics is occupied a lot of my time recently. And I'm amazed, for example, that in classical electrodynamic textbooks, they really do not present classical electrodynamics, in particular Maxwell's equations, using what I consider much more fundamental is discrete charged bodies. Now, I'm not saying point particles. That's why I keep saying discrete charged bodies. I'm trying to get away from that idea of a zero-dimensional charged point particle. But I've never seen Maxwell's equations with fields and with the potentials written for discrete charged bodies. They always go into, well, we'll change that to charge density functions and we'll change the sums into integrals. But to me, that's an additional approximation. Why don't they ever write it down in terms of sums? And then, okay, you can go and do the integration. But the fundamental is just two discrete charged bodies dynamically. And I never see that written down. So fundamental things in classical electrodynamics is very interesting to me at the moment.
Yeah, so I guess my comment would be that, you're saying that really the only thing that matters here are the charges and their Coulomb fields, and that we shouldn't really see anything that's not really arising from those Coulomb fields. Although I was thinking certainly one of the things that's mysterious about the magnetic field is that we have this induction effect whereby, if you have a wire and it's carrying current and then all of a sudden you cut off the current, then you would think that if what you were saying is true, then the magnetic field should instantly disappear because the particle is no longer in motion, the Coulomb force just comes to a halt. But we don't observe that. Actually, this induction effect, causes forces, and they die down gradually. There's something that dies down gradually after you cut off the current. It's as if something was charged up during the actual motion, and then it had to kind of like spin down. Some of our other dissidents, like David Toom, kind of expressed that like there was a flywheel or something. That
I would
flywheel. You can, after you turn off the motor, it's still spinning, and there's this induction effect kind of works like that. I mean, I disagree that that's the way it works, but how do you think things like that work? Induction.
By the motion of the charged bodies, because they have kinetic energy, and so they have momentum. Point is that
the kinetic energy is immediately dropped to zero, but there's still something going on after the motion dropped to zero.
But with the induction, you might say the source coil current goes to zero, but that induces the motion in the other coil, the transformer coil. And then that motion is acting back on the original source electrons. And then that motion is acting again back on the transformer coil. So they are coupled. And I'd put it down to mechanical motion of the charged bodies, because once those charged bodies stop, they are not acting with a dynamic coupling coefficient anymore.
Well, I'm not sure that I'm really satisfied with that answer. I mean, I can see, you know, the motivation, because I kind of disagree with the notion that the only things in play are here. Like if you have the two charges, that the only thing that's in play in here are those two charges and the Coulomb fields. You know, and partially that's because there does seem to be this charging of space per se. That once you get the magnetic field going, you can't just. There's something else going on there. Well, actually, so James, if you have some comments here, I'll let you go. Let's see, I think you're muted
Thank you,
there.
Franklin. And thank you, Franklin, and thank you, Bob, for a very informative presentation. It occurred to me that in Paul Violette's work that you quoted, the etherons are much like the quanta. And I was happy and surprised to see that in Paul's work that you cited, and maybe in your own work as well, you talk about this G gradient. Well, that was my last week's presentation, which now appears as a paper titled Motion Law, the Gravitation Edition. That's my most recent publication in the Journal of Binary Mechanics. So I just wanted to point that out, that there's a parallel here. And much like Dimitriev's work, maybe I should look into Paul's work or be in communication with him, or maybe he should know about what I'm doing. Now, additional reaction is, what is more fundamental or physical? Without quantization, I think that everybody may be going, with all due respect, may be going around in circles. Like we just raised the, Ian raised the idea, well, couldn't we work the equation starting with the magnetic field being fundamental and get what the Coulomb effects are from that? So I think what happens when you have full quantization is that some of these things, for one thing, you get both electric monopoles, those are the M-type quanta, those are the etherons that Bob mentioned in his presentation. I call them quanta. And you get magnetic monopoles, which have two directions. And so you get four kinds of objects, plus and minus M quanta, which are the plus and minus electric charge, and right and left or up and down, one direction or the other direction as far as the L-type bits, which are, I think, are magnetic monopoles. Now, let's see. I've also quantized the Coulomb, because if you take the Coulomb's equation, and when you quantize things, it changes the whole picture. When you quantize length, for example, in the R squared, it's actually the force. Yes. Now, so that's with the, just by quantizing length and now quantizing the unit of time. And here I'm concluding. I don't want to make a long speech here, but I made a few notes, and I'm at the bottom of my notes. If we quantize now time in what I call full quantization, the meaning of relative motion goes away, or it's very, very limited, because the system state at a particular quantized time point in the development of the system state can only do certain things based upon the time development laws that I presented. Okay. And so that when we're talking about the
We're having some trouble with the sound there.
relative motion, all of these are more because with full quantization, and this is my last sentence, issues, which is more fundamental, which, can we derive this from that? Okay.
Yeah,
Can you hear me good now?
I just heard the last sentence you said, but we missed like the last minute.
Well, I just heard Ian say.
Yeah, you're still cutting out, unfortunately.
Oh, okay. I talked about. You're cutting out. I'm cutting out. Well, then I guess I should just be quiet because that must be a problem on my end.
Yeah, you sound real good until you get to the good part of what you're saying, and then you cut out.
What was the good part? Perhaps there was a momentary overload in my internet service provider. What was the good part, so I can just finish up? Because I only had a few more little things to say. I didn't want to monopolize the conversation.
Yeah, I particularly like the idea of discretizing everything, including time, and then you kind of cut out. But it seems to me that would answer Franklin's question. Okay, well then what is that made out of? And then what is that made out of? And then what is that made out of? If there is a fundamental limit, and there, it would resolve that kind of infinite regression. So anyway.
Well, the last thing I was saying before I cut out was that with full quantization, and following up with what Bob said just now, is when I talked about quantizing the Coulomb force when you quantize length, because the denominator in Coulomb's equation now is just one value, the length constant, L. When we do the same thing with time, what we have then is all of these things about relative motion at a more complicated level, if you will, disappear, because the system state at a particular quantized time point in its development can only do certain things defined by the laws of the time development laws of binary mechanics. That's all that can happen. So when we ask what is more fundamental, I would have to say we've got the two kinds of M bits, plus or minus charge attribute, two kinds of L bits, right-left direction attribute along each of the three axes. And lastly, I guess that's what I wanted to say. Thank you.
Well, thanks, James. Maybe we could discuss this more offline through email or something, because that's quite interesting to me. Thanks.
Absolutely. Well, thank you. Because you see, like the work that Bob is doing, I think is very important, because it sort of maybe shows where the limits of real-time mathematics. You see where, real number. I misspoke. Real number mathematics, where we're integrating things and so forth. And we're assuming an equal charge distribution. Well, with full quantization, there is no such distribution. There are discrete quanta, the etherons. Anyway, there are other questions, so I'll be quiet.
Yeah, I do have another question or comment. We have Jeff Cook joining us. Welcome, Jeff.
Hi, it's been a long time. So thank you, Bob. I do have a question. I don't think we've ever met. It's been a few years since I've been on here. I kind of sit in on the YouTube end of it, so I never actually asked questions. So you had mentioned Occam's Razor, and you had mentioned definitions. So there's many definitions of fields, and therefore many definitions of force. So before I ask a question, I'll just kind of tell you I subscribe to the infinite field philosophy. So I'm kind of from the other end, and I agree with Ian. If you go for a fundamental field, you could pretty much mathematically start from anywhere, because they all kind of, in my opinion, link back to the others. I'm writing a book, so the question comes from this book, and your answer may help me to formulate changes or anything, I don't know. So I define force based on mathematical definition, the measurement of how much distance a given mass travels over a certain amount of time. And then a field of force, which would be the B field, or if you accept that, or gravitation, or any of the others, is the measurement of how much space a given mass covers repetitively over time. So it's a field, in my understanding, is an action force system. So if a bus is going in a circle, it repeats its trajectory multiple times, has its frequency, the bus is the moving mass, that system can get disrupted, and pretty much you can describe any sort of repetitive action as interacting in a field. So the field would be how much space a given mass covers repetitively over time. And so all fields then fall into that. Gravitation, magnetic, electric charge, all of them can actually be tied to that. So first question, oh, and then Occam's Razor. So in the scientific method, Occam's Razor doesn't necessarily have to do with multiplication. It has more to do with how many assumptions you're adding to the argument. So you would say don't have too many assumptions would be equivalent to saying don't multiply entities beyond necessity. So with the right definitions of a field of force, I believe you can actually have just one assumption and still cover an infinite field of force. And I'll give you the assumption is mathematical. I was going to try to get it so I could put it on my screen, but I'm really not sure if I'll be able to do that. So I guess the main question I have is, how do you define a field of force in the first place? And how is it different than the mathematical definition I gave, which is the measurement of how much space a given mass covers repetitively over time? Do you understand the question?
Not completely, but the way that I define the electrodynamic force would be a gradient in the concentration of these etherons. If there's a gradient, then a body would move to, there'd be there'd be an unequal balance on that body, and the body would want to move to equalize its overall shape, its overall energy content, whatever you want to call that. And that's where I think any force comes from. It's an imbalance across the body.
Okay.
Now,
So,
a field, a force field, I'm not sure that it makes sense other than through a mathematical definition, because I would not consider there to be a force at a position in space unless there is a test body there for it to act on. Then there would be a manifestation of a force.
Well, is that really true? I mean, that's the kind of thing. If the tree falls in the forest and no one's there to see it or hear it, did it happen? I would argue yes, it most definitely happened.
Yeah, well, the fields extend to all the infinitude of space, so they're all present. What I'm speaking of, and I'd like to hear all your answers, but just so you guys understand what I'm asking. So, for instance, the electric field is kilograms times mass over coulombs over seconds squared. So you can multiply it by the force, and you get the action, or dividing it. So force over the action, or force multiplied by the action, will give you the field. So you can do this with the magnetic field, you can do it with the gravitational field, and you're going to get force. The field itself is a product of the force and the action. So all of the fields have that. Even the 0-point energy field or the vacuum field will have that in a way. So that's what I'm talking. Why I call it a field of force. And the only one that actually, ironically, B field falls very nicely. The A field falls nicely. So B field, where is it here? B field is kilograms over coulombs, times time. So referring to the definitions of field of force, we would state that B is a field of force as it is a measurement of how much space a given mass travels, which is B in kilograms times mass, repetitively. Then you put it over the charge or the action. So that would be the action of the B field, be mass times coulombs. And then you end up having the mathematical definition of the B field, which is in kilograms times mass per seconds, which reduces to kilograms over coulombs per second.
I'm not quite sure, Jeff, what this has to do with all these units that you're talking about. In my mind, it's like you have the field of force, and the force is strictly measured in, say, newtons, right? On test force. So how is that relating to all these other things you're talking about?
Okay, because it is well known what interacts in an electric field. It's electric charge. It's also known what interacts in a B field, which is charge times time, so electrical current, or that would be the A vector field. So then there's a curl, which is distance, also interacts with the B field. So you can actually derive all of the fields and that match any definition of the magnetic B field or the A field or electric field or gravitational field simply by multiplying the action, which is known what interacts in each of these fields. So in gravity, it would be mass. So mass interacts with velocity, and it becomes, then you get Newton's force. So each one of these can be applied to it. So I'm not sure how we could say that one is not a field if it still has something that it interacts with, and the B field does interact with something. And in the end, they're all measurements of something. So when I hear that people would say, I don't believe time exists. Well, it's a measurement. If we can measure it, then it exists. If distance is something and we can measure it, then it's something that exists. The B field is a measurement. And then the question is, how do you define what it is a measurement of? And I define it mathematically is the measurement of how much a mass travels in a given amount of space over time. And that's what all of the dimensions describe it as. And I'm not really sure.
Are you arguing that the magnetic field is an actual thing? Because I think Bob would argue that the magnetic field, really isn't an actual thing. It's just a thing that looks like it exists, but it's still fundamentally the Coulomb force. But would you say that the magnetic field, really has a physical manifestation in space independent of the Coulomb field? Is that what you're trying to do?
I do. And then, so my question then is, how does he define fields to say that it doesn't exist if we can measure it? In fact, if we're measuring a voltmeter, we're almost always measuring the B field. We're not actually measuring voltage. We're not measuring current. We're measuring the B field.
Your question is, how can we say the magnetic field doesn't exist when we can clearly measure it as something separate from the Coulomb force? So
because in classical electrodynamics, via the Weber approach, all electrodynamic forces comes from a very simple equation, which is the force F is equal to gamma, a coupling coefficient, times the Coulomb field, all forces. And when you go and use just that definition, you can develop and derive all the experimental results that involve the so-called magnetic field. And yeah, I just said that, and I shouldn't have, because I don't know what all the experimental results are. But in the cases that I have looked at, straight wires, loops of wire, transformer induction, et cetera, Weber electrodynamics gives the same result as if you use Maxwell's electrodynamics with a magnetic field. But the force equation is so simple in Weber. F is equal to gamma times the Coulomb field. There's no need for a magnetic field. You can,
Yeah, that's why I was trying to point out that, if you look at Lorentz force law, that doesn't say anything about induction either. But, yet we have this thing you have to kind of explain, which is, because typically when you build electrical circuits that have, say, inductors in them, which is just a little coil of wire, if you don't do this right, you'll end up burning out your components, because we have this effect that, you attach the battery to the inductor, which is just a coil of wire, you disconnect the battery, and then this massive surge of electricity comes through your system due to, this effect that there is something remaining after you suddenly cut off the flow of current. And that's just a self-interaction. There's not actually any, transformer effects. There's not anything else in there. And I'm just, I can't really explain it myself either, really. But any theory of magnetism will have to try and deal with that. So I would just like to encourage you to look at that, because like I said, the Lorentz force doesn't really explain it either. But it does seriously suggest that there is something being like physically charged up or stressed or what have you in the space around the inductor, and it's being released back into the environment as it kind of spins down. And it kind of depends on, like, say, what's the material that is inside the inductor. You can make better or worse inductors depending upon what you got coils wrapped around, which also seriously suggests that there is something in that material which is being literally charged up. It's like a capacitor in some ways. And in fact, capacitors and inductors are used in tandem because they're storage energy devices, right? And that seriously suggests to me that there is something about the magnetic field that literally stores energy, right? And that would be contradictory to the view that there isn't any actual magnetic field or something that's not actually physically associated with the magnetic field, or that the only thing that we're seeing here is just the reaction of the charges moving around just due to Coulomb force. So, my other comment,
I would agree with that. I would agree with it. If I can ask one more question to Bob, and then I'll let you guys talk. Okay, I just have one more question on that. I agree that there is something more with the magnet, and it definitely is. There's something intricately very significant about the storage mechanisms of a magnetic field. But I do have a question last for Bob, if I can, on this, because I think I just want to make sure that I'm understanding what he's saying. I definitely agree there's something more to magnetism, especially in terms of inductance. So I don't believe that the B field at all induces a magnetic field or induction. I don't believe it has to do with the H field. But I do have a question for Bob. Could I one last thing?
Sure, go ahead.
All right. When you say
Questions?
Coulomb field, are you referring to the electric field or charge, which is measured in coulombs?
When I say Coulomb field, what I'm talking about is the mathematical representation of the charge throughout space, by which I mean the Q for charge over a separation distance, and then in a particular direction, radial direction. That equation giving the Coulomb electric field. Some people call it the Coulomb static field, but I don't like that terminology at all.
Okay, I just call it the electric field. I get it. And it's
the reason is you get a mathematical contradiction if you do it that way, what you just said. Because if you look at the textbooks, they start out with electrostatics and they use the symbol E, and they say E is equal to blah, blah, blah.
Yeah.
Then in electrodynamics chapter, they say E is equal to blah, blah, blah. And it's different. They redefine what they mean by electric field. So I try to be very careful, which, by the way, a redefinition of a definition is not, quote unquote, legal in math. So I try to be very careful and say the Coulomb field, and I symbolize a E with a C, versus the electrodynamic field, which is just the letter E. They're different.
Okay, so so obviously, if you're defining E and you're following that path, you can have alternative representations of this field, or let's just call it C. I'm used to looking at a measurement of charge in C for coulombs, but if you're defining, it depends how you're deriving. If you're going through a process and you define it as E in a certain way, then all of the alternative representations must equal. So if you have values of charge, if you have a value of time and distance and mass, those alternative representations should all end up equaling your C. But how you define it, I mean, like Ian was saying, you can come from a different direction and find it in another way, and it's still mathematically equivalent.
It's what you've been saying here in this session is very interesting, and I'd love to see it written down because it is a little bit hard to follow. A little bit hard to follow mathematics just by talking.
I know. All right,
but it's
so
very interesting what you're saying.
Well, what I basically, I'm writing a book, and I'm referring to the book, and I should be just discussing, because it's a lot easier to share. All right, so what I'm saying is, if you go to Wolfram Alpha, which is a free calculator, and they do physics derivations and things in mathematics, and you type any function, they're going to give you about 6 different alternative representations of all that equal the same value.
Right.
So that's all that is.
That's why I was showing in one of my slides the so-called multipole expansion, which is similar, not exactly what you're talking about, but that gives you an infinite number of terms. And so is each one of those infinite number of terms to be considered a separate field? I don't know. It's a mathematical representation the way that I think of it, and not necessarily physical.
Anyway. All right, so let me give you a physical example then. All right, so if the B field doesn't exist and you're not actually feeling, all right, in an electric coil, let's say you have a coil wrapped around an iron core. So, and you have then manifesting around the iron filings, you'll see a curl around the outside. This is the physical manifestation. Inside, you have the magnetic vector potential, which is actually considered a field of sorts, and it's going in parallel with the electric field if you map the the left-hand rule and all that. So if, however, you take a toroid and you wrap a coil around it, then the A field is going to manifest out around. The B field then becomes linear or collinear with the electric field. So does also the A field not exist?
Yes, I would say the A field does not exist. And the reason is, for example, I can write B is equal to velocity cross product Coulomb field with the units 1 over c squared. So every time you say a B, I got a loop of wire and it's generating a B field, blah, blah. I think he's saying velocity cross Coulomb field. Every single time, in any case, in any experimental case that you think, because I haven't seen an exception to doing that. And therefore, every B is really a Coulomb field.
But we don't see, a static charge being attracted to that Coulomb field, right?
The charge would be attracted and repelled the electric field, yeah.
If you have if it was a Coulomb field, then in any Coulomb field, we'll see a static, motionless charge be attracted to and move into that field. But this is the mystery of the magnetic field. is that if it's a Coulomb field, then, how come it doesn't have any activity at all on a stationary charge? That's really the big mystery here, right? If it were a Coulomb, it has to move, right? But
I thought that they did. So if you have an electric charge out in space, and you throw on an electric field, that charge is going to move across space to it or away from it, depending on how it is, just as two magnets would repel. So the action.
That's the way Coulomb fields work, right? But the way magnetic fields work is that you have
they interact with something. Yeah, they would interact with something else.
You have the most powerful magnet in the world. You put a test charge out in space somewhere stationary to that, and it will not move. It does not feel any force at all.
Right. That's because they have
the Coulomb force.
Right. So what I would say, is that field does not interact with that action. So the charge would be the action in gauge theory. I'm coming from gauge theory framework. So in gauge theory, the action would be that which interacts with the field. So electric field and gravity may have some crossovers, but pretty much not. I mean, mass is that which interacts in the gravitational field, and with electric field, that which interacts with the electric charge. And so charge would then be attracted. A magnetic field, B field, or let's go to A field, it's more fundamental, would be electric current. So if you have electric current traveling on a wire, it would be attracted to the A field. And if you have electric charge times curl, then that would interact with the B field. And these experiments anyone can do, but they don't interact with, so that moving electric current does not interact with the electric field. Just the charge would, but charge over distance, or what is amperes? Is it charge over distance or charge over times distance? Anyway, so it's electric current. Charge per second, sorry. The charge per second is that which interacts with the A field. And charge per second times distance would be that which interacts with the B field. So you're not going to get any interaction between, every field has a unique action that it interacts with. And because dividing them to the two, you get force in newtons. So that's why I wouldn't interact with it. I don't see that as saying they don't exist. It's just they don't resonate with other fields.
And that's why I want to see it written down, because I'd then like to take the equations that you're talking about and see if I can express them in terms of a Coulomb field. Can you factor out a Coulomb field, a Q over R kind of factor in all of those? And if you can, then what you're doing is using the Coulomb field and coupling it in some way to the charged particles.
All right. How about this? I'd like to get your email, and I'm going to send you a page of a chapter of this book, and then see what you think. And you don't need to respond to anything. You can just read it, okay? And then it'll be done. All right. What's your email address?
Do you have a website? No, not yet.
No, I don't. But I've done 3 video conferences on this, but they're probably with the NPA. I have in volume, the Proceedings of the Natural Philosophy Alliance, volume 9. Is a paper on this, but also there's a video conference where I presented at New Mexico, where I discuss it, and it has all the equations. So there's many things online. Not on my, I don't have a website, not this time, but yes, I can.
Maybe if we Google you, we can find your stuff.
Yes, let me give you
I've put my email address in the chat. Since it's the private chat, I don't know which chat you're looking at.
Yeah, you should be able to look at the private chat.
Let's do Jeff Cook, Albuquerque. I don't know how to spell Albuquerque. Screw it, I'm not gonna. New Mexico. All right, NPA. And then I don't remember the year. It was the year that John Sturl was there. It was the year that and Greg Volk was there. What the heck? Let's see. I'll find it. All right, let me log off. I'm gonna log back in. You guys take other questions, and I'm gonna come back with an exact link. Okay, I'll find it because I've watched it before. All right, give me a little time to shut down. I'll be back. Okay.
No, you don't have to shut down. You can just open up another browser window. You don't.
All right, hold on.
Don't want to lose.
May have to.
You do have another.
This whole question of these different fields, whether they are merely different manifestations of a primary field, or whether they are separate entities, is rather philosophical or even semantic. I mean, it could well be that there is some fundamental field that hasn't really been defined at the present time. And in terms of which the gravitational field and the electric field and the magnetic field could very well be formulated to be different manifestations. Now, as I've said, I wouldn't, a bit like Jeff, I wouldn't say that therefore these other fields don't exist. You might say they're entities, they're different manifestations, you could say, of this primary field. So it's really a philosophical question that I think Bob has raised in looking at the magnetic and the electric field as being maybe correlatives.
Well, I don't think it's philosophical. I mean, I think that is your key point, which is that maybe these fields are all kind of the manifestation of the same thing. But, you have to answer the question of, well, if that's a manifestation of the Coulomb force, then, why did it act differently? And any one of these forces,
Right.
could be called basic. And I think at some point someone is,
Well, what I would like,
magnetic field basic. Someone calls the magnetic field basic. Someone may call the gravitational field basic.
it would be interesting to know of an experiment that can only be explained by the reality of a magnetic field, that cannot be explained by the Coulomb field and a velocity cross Coulomb field, but a real physical magnetic field, and it's the only way to get those experimental results. Then I would, seriously consider, okay, the magnetic field is absolutely different. If there's no way to explain it any other way, and you do have these experimental results, then I guess we have to say, okay, there's a magnetic field. But I haven't seen that yet.
I keep on pointing out that induction,
Yes, which is fully explained in Weber electrodynamics. Induction has been fully explained in electrodynamics.
and how do they explain the persistence of basically the energy storage mechanism?
Right.
The
RLC circuit, resistor, inductor, capacitor, oscillations in an RL circuit, has been detailed by Professor Assis using Weber electrodynamics.
And how does he do it?
I'll have him on and ask him.
Without actually invoking that there's something being stored in blank space. There's something it's not a capacitor.
He would say that there's no fields. He'd say that there's no fields, period. There's none. It's just action at a distance. You have an action of a source particle on a test particle, no fields in between.
See,
that's more of a literal interpretation of Weber electrodynamics. I happen to prefer my field interpretation of Weber electrodynamics, but no, have Professor Assis on and ask him.
Well, this is where I think that you're not understanding what he's saying. He could be blowing smoke, and I think he probably is. I think as a dissident, I mean, I'm giving you that thing that I think you need to look into. This is the thing that's mysterious to me. It's like I'm not 100% sure I can understand how this energy is stored in the magnetic devices. But it would, as to your point, is that if we can show you an experiment that shows that there really is something else here, and that would be the something else, that magnetic fields appear to be able to store energy. If they were not a real thing, how can nothing store energy? There has to be some physical mechanism to do it. So I would, just as an encouragement to you, if you've not looked into it, maybe you can explain it, but don't rely on someone else saying that Weber's electrodynamics explained it without, not actually looking into it yourself.
Yeah, I've looked at his paper. I reproduced the calculations, but that was like years and years ago now, and it's just not fresh in my mind. But it was enough for me to say, okay, he's done that. He's taken a look at and explained RLC circuits using Weber electrodynamics.
Yeah, and once again,
and
explaining might be you just replicated and explain,
Yeah.
you know, the how, but
Yeah.
still, that's still not what we're looking for. We're looking for
Okay.
why.
Okay.
Because anybody can explain it and do the RLC circuits. That's just, you know, basic, you know, electronics. But that's not really what we're looking for. We're looking for why is it that thing, that little device that we have, that thing appears to store energy just like a capacitor would. Really, it's you put energy into it, you
And furthermore, the
charge it, and it comes out. Right? There's
magnetic permeability, which would come into the equation in regard to the storage of magnetic energy, is not just a simple function of the electrostatic, the electric permittivity. It's not like E squared epsilon naught squared or something. Now you might say, well, I say, well, it brings in other factors. It's not simply that. You might say, well, yes, but it's just C squared, you know, comes into the equation. But that's another factor. Epsilon naught is not simply a function mu naught is not simply a function of epsilon naught, which you might imagine if a magnetic field, the non-existent magnetic field, were simply just derived from the electric field.
so we do have some comments here from the live stream. Bob, you got some questions here. Does Bob's electric dynamical theory involve an explanation of transverse waves and of longitudinal waves? So, Bob, what do you think about this whole wave business?
Right. Oh, there's in my presentations that I've done previously, I showed where longitudinal waves and transverse waves come from. And longitudinal waves are simply along the direction connecting the two interacting charged bodies. So if I change that distance between the two charged bodies, then the force is going to be along that line, and it's going to be a change in the force, and the change in the force is a wave. So there's definitely longitudinal waves in classical electrodynamics. And then if I have, for example, a dipole antenna, it looks like the sum of the forces is or has a transverse component to it. And so you can add transverse components to electrodynamic waves.
So you're just saying that transverse and longitudinal waves exist in electrodynamics, right?
Yes. Yes.
Just like transverse and electrical fields, I don't know, exist in various mediums like air. I did have an interaction recently with some people on the email. You know, the claim is that transverse waves do not propagate in fluids, and therefore the argument is since light has these transverse components in it, that the medium of light must be a solid, right? But I just realized the most obvious counterexample, which is that if you've seen the wave tank, right, that is definitely a transverse wave. You know, the wave goes this direction, and the waves themselves move up and down, right, in the transverse motion. That is clearly a transmission of a transverse wave through a fluid, right? So I just use that to try and contradict this whole idea that the fluid that the thing that the medium that light travels through has to in some way be a solid, because although that's kind of strange that I even say that, because I don't think that light transmission itself is transverse either. So that's my other claim to fame, that I don't think that the transmission of light ever involves anything that's bobbing up and down like a cork would in a wave tank. I don't think that it has anything to do with that at all. But that's kind of a side. Maybe that kind of answers a little bit about what Dennis was asking about, you know, this whole transverse longitudinal wave. I mean, other people, like I think maybe Cornelius also has a comment, you know, saying that even transverse waves are actually longitudinal in nature. It's just a matter of what direction the things are getting pushed, right? So there really aren't any actual transverse waves. They're all complicated composite longitudinal waves, because in the end, that's the only thing that mediums can do. They can be they're compressed, they're rarefied. That you have some components going this way or that way is kind of irrelevant. It's still push. It's still a rarefication, still concentration, still.
That's what I put in a presentation a year or so ago. Can I share my screen real quick?
Sure, if you'd like.
It will be a short. Click on that. Click on share.
Okay, we got your stream.
So here's how I explain transverse waves in a presentation I did a year or so ago, where you have on the left, you have multiple sources, a charge body and a charge body, generating only longitudinal waves onto a test charge body. If you look at the direction of the forces, you got the force due to this plus charge, and you got this force due to the minus charge. You sum up these forces on that test body, and what do you get? You get a net force which has a transverse component, but that transverse component came from longitudinal forces. And that's, I think, exactly what you were just saying about, who was it, Cornelius, you said?
Yeah.
That the transverse stuff is only coming from the longitudinal. And I would totally agree with that. And then in this presentation, I have all these derivations of why the traditional proof of transverse waves goes wrong. But that's for another time.
Okay, yeah, I think that goes directly to Dennis's questions about, do you have explanations of transverse waves? And certainly it sounds like you have gone into this great more detail than I thought you did. You did. So
I sent a link in that in the private chat really quick. I sent a link to that video, but I can't get it in the public. I don't know why. So I go to the chat. It says I have YouTube. I have if you do a search on experiment on the linear increase in efficiency, it'll come up. It'll be the first video. But I don't know how to put it in the live comments. Do I have to be on Facebook for that?
Yeah, or I could put it up. Let me just copy it over.
So if you just go to YouTube and then type experiment on the linear increase. I think any amount of those words is going to bring it up. So just those words alone will bring it up. And the important time period specific to Bob's question is at 24 and 32 seconds or around there, about 24 minutes in. And it discusses that. So it's kind of like the general form of fields of force.
Okay, let's see here. Now, so Cornelius, you did have some other comments here. Let's get to those. So he's saying, wait a minute, that was the previous one here. Bob said it correctly, fields are mathematical measurement quantization only. I think I disagree with that, but I was wondering what you were thinking, Bob. Is it only a mathematical thing?
Well, I consider the Coulomb field to be physically real, but all other fields, quote unquote fields, I consider to be mathematical niceties, if you will, that allows you to manipulate and calculate things easily. But when you then try to impose a physical reality to those mathematical things, I think you run into problems. And so I try to stay away from that. I try to say Coulomb field and any other quote unquote field, I try to say function as in a mathematical function.
So you would say, like, gravity is a mathematical function? Is that?
Sorry, I was restricting my comments just to electrodynamics.
But presumably you do
So you would say gravity.
gravitational field to be fundamental as well. Do you, Bob?
I have no idea about what the gravity field is, except for, as I say, I like Paul Laviolette's reaction diffusion system model, which has both the electrodynamics and gravity. And in that model, gravity is related to what he calls G-ons, and whatever G-ons are. And the gravitational force is then a gradient in the G-on concentration throughout space. And because there's a gradient in that concentration, things will attract each other like quote unquote gravity field. That's about the best model for me, best model that I've come across for gravity.
Okay, although that was my point last conference.
I might add a comment here.
Don't cause forces. So go ahead, James.
Yeah, for about 45 minutes now, we've been discussing all kinds of fields and forces. Now, we define a force in terms of the three fundamental units of measurement in physics: mass, length, and time. I use in my fundamental constants mass as a index of energy, as opposed to inertial or gravitational mass, which is another matter. But the point I'm making is without full quantization, much of our discussion sounds more like engineers using real number math, and ideas like fields and to describe phenomena and maybe to design things, more like a discussion among engineers than a discussion among physicists, more about engineering than about physics. So that if we're throwing around, what is this force, or that force, or is there a force field? Well, it's defined in terms of the full quantization parameters of mass, length, and time that have been presented. And so there's what I'm saying, and to conclude, is that, like, for example, gravity theory, people will try to quantize one of the things, like, say, length, and the little loops that they have in loop gravity theory, not all three parameters. Or they'll quantize just a little particle, which I call a quanta, as a etheron or a G-on, and talk about G gradients and so forth, which is similar to what I'm talking about. So in other words, people are tiptoeing into the waters of full quantization by quantizing one thing or the other, like length and loop gravity theory as an example, or perhaps energy in terms of these etheron particles and so forth. Why don't we just go with full quantization and do the full Monte, as I call it, full Monte? That was the movie.
Well, I'm not quite sure I understand your comment there. I mean, I personally think that quantization is a very important concept, so that you don't get infinities running around in reality. But it once you get that past that, and once you be able to establish, say, what an electron is, then that becomes less important. It's like, okay, that sort of forms the foundation, but the actual building is still the stick in the woods and the thing that you put your furniture in. And I mean, I don't know what quantization is important, but it has limited applications, I guess what I'm trying to say. Would you agree with that?
In my treatment of quantization, as some of the people here know, and the viewers of the videos know, I've been able to derive from first principles the most important unexplained data in physics: the speed of light, Planck's constant, electric charge, electron mass, etc., electron magnetic moment, etc. So it does matter. In other words, it produces results.
Yeah, but
Whereas all this
doesn't
talk
it
about
have an
which
actual form?
field is more fundamental and which mathematical nicety is more appropriate, to quote Ian, is, I think, talk among engineers. You know, like perhaps we should be focusing on let's design a new magnet or something, rather than talking about what is the fundamental physics involved here. Because all of us talk about, in other words, what is the meaning of a field? Without full quantization, you see, people drop their jaw when I say the electric field is the distribution of the M quanta. And they drop their jaws because some of the locations, the bit locations, which are cubes of size L, which is the fundamental length constant, some of these locations don't have M quanta. They only have L quanta in them. So you see, the field is not like even a continuous thing. It's fully quantized. And so to pretend that it is a continuous thing is a really fundamental mistake. And I just am concerned that so many people are really wasting a lot of time with this real number math, which they ought to leave to the engineers designing magnets and motors and things like that, and radio transmission towers and things. But the physics with full quantization, which is what has produced these kinds of results I mentioned, involves full quantization. Rather, you know, and people are tiptoeing in the water with LGT, just quantized space, or they're tiptoeing in the water in one way or the other. Why not quantize them all and start to get some real results? And we leave all this stuff about you know, which field is real, and you know, is it, you know, what's the physically real field and so forth.
James.
Yeah.
James, I need your binary mechanics for dummies book. Please finish it.
Well, each paper I try to present stuff, and like the last paper on the gradient, I presented last week here. During the week I wrote the paper, and it's now up on the journal, the binary-mechanics.com site, and as the top paper. And then I come here today and find you, Bob, talking about Paul's work, talking about a gradient of etherons. I assume the
Right.
geon is a kind of etheron, that the generic particle is etheron. And
Yep.
and so you see how people are tiptoeing there.
That's
and
one reason
getting
why I
the
put it
same
in my
result.
presentation. I put it in my presentation because of that. I wanted to make the connection to what you were saying last week, but I don't know your work well enough to go beyond that yet. Someday, but not yet.
Okay, well, it helps me to hear people's comments so that I can learn to present it better. Like, for example, my latest paper with the figures that I showed the figures here last week. So they're in the video from last week, and they're in my paper. On Dimitri's work, but I had some introductory, like, schematic diagrams to try and present what I've been saying in words, that the basic motion law is that objects tend to move in the direction of higher quanta density. And that's exactly what Paul Violetta is saying. So different people are tiptoeing, I think, in the right direction, and it's educational for me because I want to give credit where credit is due. If someone has this idea in common, I want to cite them and say, you see what I'm saying? I'm not alone in saying this. There's somebody else that has, probably smarter than me, Paul Violette, that's saying the same damn thing. You see the point? So these discussions are very useful. I mean, thank you, everybody.
Okay, we've got some other comments here from the live stream here. I think they're still discussing a little bit about the whole transverse versus longitudinal thing here. So I think Cornelius is making the point here that the transverse wave that I'm talking about exists in the transition zone between a fluid and a gas, and that's where we observe the transverse business, which is kind of, I guess, a counterexample saying that the fluid doesn't carry the transverse wave. I would counter to say that, yeah, we see it between a fluid and a glass. Both of those are non-solids. And actually, I think one of the characteristics of transverse waves, like most common example, is a rope that you wave up and down, right? And you see that all transverse waves seem to have this requirement that there is some boundary, right? That is where the transverse wave propagates, like between the rope and the air around it. There's very few kind of transverse waves, and I think this is why the people who are stuck in this idea that transverse waves are only propagated by solids. There are very few where that may not actually be the case, like an earthquake wave. But even there, the transition between the ground and the air above it, you see that going up and down. That's still a transition, and we still see that the ground movement is up and down. But that is exactly the same thing that's going on in the wave tank. If you were to look at the molecules underneath the top of the water, you can see that they are actually physically moving up and down. You put a bobber on that wave, you can see it physically moves up and down. I mean, there are, that's just the nature of the thing here. So I wouldn't say that that observing a transverse wave between the interface between fluid and gas really has anything necessarily to discount the assertion that transverse waves travel through fluids, right? Versus solids. I personally think the entire argument is specious, really. But you have the additional comment here that transverse wave is different from longitudinal wave, but they each have longitudinal and transverse wavelengths. And I would agree with that in that definitely things like light waves do actually have, must have transverse components. I mean, there's definitely some component that is not going in the same direction as the general velocity, general direction that the wave is traveling, right? You got the wave traveling this way, but there is some components which are like, not pointed strictly in that direction, right? There's some other components pointed some other way, and you can recover that direction, right? But my argument would be that, a pencil, has transverse components. If I throw my pencil, it's like a broomstick. I could, filter out the left and right directions so that only the up and down directions remain. And that is kind of what polarization is like. So if I had a filter, which I throw my broomstick some arbitrary direction, which would limit it to just the up and down vectors. And then I put another polarization filter, which would only allow the horizontal vectors, then that would completely block all of my broomsticks, right? And that's exactly what polarization is that you're just reducing the components. Any vector can be decomposed into various components. And that's all that the transverse partness is, right? It's just decomposing the vector into different ways. You've got the vector that represents its motion through space, and then you've got some other vectors representing its particular direction that's away from the general XYZ axis, I guess. So does anyone else have any comment about that? I mean, do transverse waves really exist? I'm kind of saying that they really don't. It's, I guess, would be my point. That saying that transverse waves can only propagate through solids, I think, is now completely ridiculous, right? But let's see. So Cornelius has some other ways. So the ether is physical. All fields are measured of the amount of gradient in specific patterns of tension waves within that medium that manifests themselves as various forces. Anyone have any comments on that one? Bob, do you say to that? That's kind of a mouthful, but what do you think of that?
Well, I'm sorry, kind of went off on something else. So I don't have anything to say at the moment.
No. I mean, I would agree definitely that the ether is physical. That's why I keep kind of harping on this magnetic fields can store energy thing. Because in order for it to store energy, there has to be something physically there to store the energy. Nothing cannot store energy. So I would say whatever the magnetic field is, it must have a physical manifestation. And as an etherist myself, I'm thinking that that ether must be capable of storing that energy. And in my viewpoint, I think that the magnetic field is basically an orientation of the dipole particles. I mean, I think the latest analogy I would have to this is, say you fill space with compasses, right? That's just a dipole thing, right? So you fill all of space with a compass with compasses, and what you have is that whatever causes the compasses to immediately come in. So and then you put something in there, I don't know, like another magnet, which aligns all those things so that they're all pointing the same way, like you stuck a magnet in there, right? So, and then as you go further out, each compass, which is aligned in one direction, is also a small magnet, causes the other ones next to it to align to it, so on and so forth until it gets weaker and weaker and weaker. So that would be an example of something which is physically present. So in order to, say, address the induction thing, once again, I don't 100% understand this, so this is like, half of it's hand waving. But let's say you have those compasses and they're all aligned, and then you remove the thing that causes the alignment. And it will take some time for those compasses to kind of randomize, to start pointing whichever. If they were in the Earth, they would start aligning back to the magnetic field of the Earth. But if you're in space, no magnetic fields, they would just kind of eventually move back. And that, I believe, is the actual storage mechanism, that when you have all these aligned fields, that's a higher energy state. And when you stop the thing which is causing the alignments, then that decomposes slowly, and it still injects energy back into the system. Once again, that's half, that's kind of crazy, and not really a complete explanation, but it's something like that I think there is something physically, the ether is physical. Yeah, I agree, it's totally physical, but there has to be something like a compass, something dipole, because this is the two things that magnetic field has to represent. There has to be a vector direction, definitely vector direction defining the north-south. And then there is a magnitude, right? So some way there has to be a magnitude and a vector direction. And only physical things can represent that, I think. So that's kind of how I feel about that. Anyone else, like Ian?
Well,
do you have a comment? Do you think that?
I agree with what Franklin just said. Those are the L-type bits, and my paper on magnetic pulse moves both positive and negative charge in the same direction. Speaks to that point. And the injected magnetic pulse was adding L bits, all pointing in one direction. Okay. And that's your magnetic field. And since it was moving both charge types, plus and minus, in the same direction, unlike an electric field would do, the opposite charges would move in opposite directions. And there's another paper showing that. But the electrons moved more than the positive charge proton quanta in proton bit cycles, which means that these L bits are produced, if they're a magnetic pulse, are producing a polarization. Now, my question for Bob is he showed some magnets with north and some bar magnets with north and south in his quite interesting presentation, and I'm wondering how he explains in terms of just electric field the fact that these bar magnets behave the way they do when they don't have any net electric charge measured at least macroscopically. That's a question for Bob if he's still here.
Yeah, I'm still here.
Okay, wonderful.
That was a long question, right? Do you understand that, Bob?
Partially. Although the bar magnets are electrically charge neutral, the dynamics don't cancel. So you have a velocity dependent term multiplied by the Coulomb field of each individual discrete charge body making up that solid. And
Yeah, you didn't explain that. I missed that. Okay.
Yeah, that doesn't sum to zero.
It doesn't sum to zero. But then again, you've got your second and third, your first and second derivatives with respect to time. But if you quantize time, all of that goes out the window. That's more of interest to engineers, okay, and at a macroscopic level, let's say. When you quantize time, what happens at a particular tick or time point in time is the laws of time development of the system state are applied, and they can affect only what the system state is at that time to produce then a time equals 1 from time equals 0 new system state, so that all of this analysis with first and second derivatives and so forth, I think that's more for engineers, because if you quantize time, there is no second and third derivative. That's more a macroscopic view of what's happening at the more microscopic level when you do quantize time. I hope I explained that for dummies, but there are no dummies today here.
Yeah.
They're all geniuses here.
All right, so we're getting towards the end of the conference here, so I wanted to get in these last couple comments from with here. So he says quantization is due to unbounded volumetric resonance and harmonic entrainment of waves. And I guess that's one for you, James. What do you think?
Quantization is due to unbounded volumetric resonance and harmonic entrainment of waves.
I'm not quite sure that makes any sense, even as an English sentence. But
okay. Well, what my general comment to Cornelius is, you are firmly rooted in the 20th century, and this is now the 21st century. In the 20th century, love for the use of real number mathematics to describe phenomena, which, by the way, can be quite useful for engineers on the macroscopic scale. But it doesn't have a whole, like harmonic entrainment of waves, resonance. Well, those are all things that involve many units of time. Okay, and so you're using fantasy mathematics in the context of full quantization. See, when you tiptoe into the water of full quantization, it's sort of like puberty. There's no turning back. There are certain mathematical consequences which are inescapable, like a maximum energy density, for example. And all of these other things are sort of left behind as sort of your adolescence and childhood in the study of physics, in my opinion, with all due respect.
Now, I'll notice, I'll have here Alistair. So Alistair made the comment here in the private chat that math is not the path to the answer. So, Alistair, did you want to comment on that? Did you have a question for Bob? Do you think he's taking math too literally?
Well, what I know is that if use the hypothetical or the proverbial turtle. Is my volume good?
Yeah, we can hear you.
All right, so use the proverbial turtle. Pretend the universe is made out of turtles. All right, so tiny, tiny turtles. And then they're all spinning. So now you got tiny, tiny spinning turtles. And those are the units. If those are the units of existence, a spinning turtle, then you try and figure that out using math. But in math, we always want to cut things in half and split them and divide them. How the hell, when you find one is a spinning turtle, how do you cut that mathematically? You can't. So then you have to try and describe mathematically a spinning turtle. How do you describe a spinning turtle? Half of it is digital, it is one turtle, but part of it is analog, it's motion, which is continually divisible because it's a single unit, but it's spinning. There's no further quantization of the unit one, but it has an analog component, an infinitely divisible component because it's in motion. Mathematically, how can anybody ever hope to manage to arrive at the nature of a spinning turtle because of the fact that when you cut it in half, a turtle doesn't have two equal halves. It has a front and a back, or a left and a right, or an up and a down.
Have you heard of spherical cows?
Who what?
Spherical cows. It's kind of like a science joke.
Okay.
Which is that you have the farmer and he's got this problem and he asks it to the physicist, and the first thing the physicist says is that let's assume the cow is spherical, right?
Yes, so that helps with the nature of the problem, is that mathematically you arrive at a unit. Math is based on units. Somewhere there has to be a 1 and a 0 that set a scale for the mathematical system. And when you're 1, your single unit, your physical unit at the root of existence is a turtle in motion, and 0 is no turtle in motion, and 1 is one turtle in motion, I say, if you think you're going to manage to figure that out mathematically, good luck. Instead, you got to try and come up with what could that turtle possibly look like, take some shots at it, and go from the other direction. And that is why math is going to continue to fail to find the turtle. It's the wrong approach. Use it for confirmation, not for conceptualization. It's just my suggestion and my opinion.
Oh, I would totally agree with that. I mean, math is a way to make predictions, not
or describe things.
Yeah, it's not, and that should be. It's like string theory is like the opposite of that, which you literally take math and it's like everything is described in math, and it's not. It's meant to be a physical thing, but it's not a physical thing. It's things on a chalkboard, right? It's not.
And it can be used to derive things and point to things. But when you start getting into units that are in motion, you have to really think 5 times before you make conclusions, I suggest.
Okay. All right. Thanks for your comment.
I think I could, if we have time, I think I could tie that in with what Cornelius wrote about his quantization. Do we have time?
Sure. Do we have
the quote about
here? Not many.
I'll make it quick. Can you pull that quote back up? Cornelius's comment? Yeah. All right. So I think proof is something very alien to the scientific method, even though it's at the foundation of mathematics. So mathematicians can and should be, mathematics could be applied to the study of science. That backs a particular theory. It does not necessarily be a reflection of the real world, the mathematics, like you were talking about string theory. So the equation may be correct, but it may not apply to the natural world or a particular phenomenon. So mathematics seeks proof, as proof involves facts, but facts are just scribbling on a page without understanding. So science seeks truth, which leads to the understanding of these facts. That's the difference. An example is what Cornelius brought up, is he's speaking of the quantization of the ultraviolet catastrophe. So if we're all familiar with this, where equations were used that were applicable to many studies in chemistry and other sciences, but didn't happen to work out correctly in terms of black body experiments. So when he's talking about, I didn't see his quote, I was going to use it word for word.
Let me put that back up for you if you want.
Yeah, and then so that's exactly right. So so when you have a black body, the body has to resonate with the light frequency. Once it resonates, whether it's slowed from time, it outputs at a constant frequency. It outputs, and that would be the black body experiment. So that was what was called the ultraviolet catastrophe, where where this is the birth of quantum physics. So it was able to describe why is it coming out at constant frequency. It was when that resonance and harmonic capturing of the waves in the black body. So what they tried to do is design a body that would never let light out. So they kept angling to try to keep it in the box indefinitely. And so what happens, it seems light is claustrophobic. It doesn't want to stay trapped. So it comes out, it lowered its frequency or to escape, and that would be then quantization. So I think what Cornelius is saying is once you trap those waves in a certain way of volumetric resonant chamber, then quantization comes out. And perhaps that could be what is happening at the atomic level where everything seems to be quantized. And when you have a system in resonance, you're going to get light temporarily trapped. It goes in, it resonates, and then comes out in a different frequency. And I think that's what Cornelius is saying. But it does illustrate how mathematics failed because it was not a reflection of reality. So it was science. It seeks the truth. And science is kind of like math. It works every time, but it doesn't necessarily mean it works in the physical world. Science doesn't care about that. The only thing becomes fact if it's repeatable over time. So so we would say the universe is always in flux, and the winds may blow differently one day to the next, and therefore it's always changing. Math is constant, and therefore can never exactly represent the real world. So, but if you have an equation that works with gravity, yeah, you can apply some equations to it. And for engineering, it's essential. You need those measurements to build anything. So that's what Cornelius is saying, I think, and how it ties into math. Sorry if I went on too long.
All right. Well, we are at the end of time here. So thanks for everyone for participating. Just to summarize what we were talking about this week. So Bob Gray brought us a presentation on how he believes the magnetic field is working. I mean, I think the main points were that the magnetic field is just a manifestation of the emotional Coulomb field. And he showed that, he can derive the standard Lorentz force law in terms of that. So it would seem that you can explain everything just in terms of motional electric charges, which is, Weber's whole shtick, I think. And then we just started to discuss, what back to the top of like, how is the magnetic field actually working? And in particular, we did bring up the topic of, how does induction work? Induction would seem to contradict this picture that it's only the motional charges that are involved, because we can seemingly charge space with a magnetic field. It somehow holds energy. So we discussed a little bit about those topics, but most of it was spent just, talking about the nature of the magnetic field, and hopefully we'll go and maybe figure out what's going on there. But that will do it for this episode of the John Chappell Natural Philosophy Science Chat, and hope to see you again next week. Invite all your friends. All right, bye.